Yes, in this short video, I'm going to discuss about canonical transform. What are canonical transformations? What are the equations of canonical transformations? Examples. For example, we'll take up example of what are generating functions that would lead to canonical transform. Symplectic approach, uh, Poisson bracket, and other canonical invariants we will see in another video. Okay, so this we will restrict to just the canonical transformation part. So basically in classical mechanics, what we do is to solve a problem, we actually uh, find solution of a differential equation, right? So be it Newton's equations of motion or Lagrange's equations of motion or Hamiltonian equation of. But there is also another technique in which we just simply transform the coordinate system from some old coordinate system to a new coordinate system that preserves the mathematical form of Hamilton's equations of motion. Okay? You're familiar with Hamilton's equations of motion, right? Which means the new coordinate and new momenta are also canonical variables, uh, and they allow you to understand the problem as it is. But many times this transformation leads you to solution directly. First is the transformations which will preserve Hamilton's equations of motion. It's a transformation in phase space. Phase space means coordinate and momentum space together, right? Then it would have a structure which would be same as the old system, and they are connected by what you call as generating function. I've already told you why are they useful. And many times when you make a transformation, you find that in the new coordinate system, your new Hamiltonian is independent of a particular coordinate. Okay, so that becomes an advantage because then the corresponding momentum is conserved quantity. So how does it work? You transform, all right? Poisson bracket, we will be talking about it in the second part, so we will ignore that part. But basically, when you use a generating function to transform from old Hamiltonian to new Hamiltonian, old coordinates to new coordinate, the generating function can be function of old and new coordinates, or old coordinate new momenta, or old momenta new coordinates, or old momenta and or new momenta. So it depends on the convenience and need of the problem. So in essence, it's a coordinate transformation in phase space. Okay, and that allows you to understand the system better. I've already told you that suppose if you make a transformation such that the new coordinate capital Q is cyclic, then the corresponding momentum is a constant of motion. Okay, let's say alpha, right? And then your new system of Hamiltonian and with new coordinates and momenta still obeys Hamilton's equations of motion. So your Q dot will be dou K by dou P, which in this case, let's say, is since uh, P is a constant, but suppose if you differentiate with respect to that constant, you get say omega. Then your Q will be integrating. This will be omega t plus beta, where beta is of course constant, depends on initial conditions. And so your transformation has solved the problem because the new momenta is constant and the new coordinate is omega t plus beta. You have solved the problem. All right. So this is just a simple example. You can have a little more whole example, more practical. For example, if you want to see a more practical problem, then you have a central force problem. In central force motion, especially when we are dealing with planetary systems, motion is restricted to a plane. All right. And in a plane, you can use Cartesian coordinate system. and corresponding momenta. But then in this case, there is no cyclic coordinate, right? So your potential will depend on, let's say, if you take gravitational potential, it's 1 over r. So it will depend on root of x square plus y square. And therefore, it depends on both the coordinates. So they are not cyclic. But if you take circular polar coordinates, r and theta, then it turns out you may have actually seen the problem solved in circular polar coordinate system, that coordinate theta is cyclic. Your Hamiltonian does not depend on theta, and therefore the corresponding angular momentum is a constant of motion. Now, by simply making a transformation, you can see that your angular momentum is going to be a constant, which if you are actually using Newtonian equations of motion, then you will, or Lagrange's equations of motion, you will actually need to do some integration to realize that L is a constant quantity. But in this case of in this kind of situation, this technique, you immediately get that angular momentum is a constant of motion. So you have old coordinates and old momenta represented by small q and small p. New coordinates and new momenta represented by capital Q and capital P. They are just the symbols. But for example, practically, it could be xy going to r theta of transformation. Uh, then, of course, for Q and P both to be canonical, uh, with the new Hamiltonian, they must obey Hamilton's equations of motion. So Q dot has to be dou k by dou P, of course, new momenta, and Q dot is the time derivative of new coordinate. And similarly, P dot will be minus dou H by dou Q. Now, this is a must. It's a requirement for your system to uh, be canonical. And of course, you have Hamilton's equations of motion. This is only academic importance, but you can see what we are doing. So if your new system also obeys that variation principle, the old system also obeys variation principle. So we say that, look, the integrand, one of them has to be proportional to the other one. So in this case, we are saying the old one, lambda times old one, is new one plus time derivative of a function. Okay. Now, since it's a time integral, and therefore we have to put this time derivative of a. It's just a mathematical requirement. Now, this lambda which we have taken is actually called scale factor. For example, if you take new coordinates to be mu times old coordinates and new momenta to be new times old momenta, then your new Hamiltonian will be mu times old Hamiltonian. Okay, so this mu product plays the role of your lambda. It's a scale transformation. So you have scaled your coordinates. Okay, but we will be confining our self to situation when lambda is 1. Okay, so if lambda is not 1, then it is an extended canonical transformation. But we'll restrict ourselves to simpler situations when lambda is simply 1. So you can see the equation for the first one on the screen that has to be obeyed with lambda equal to 1. And in that case, what happens? Right? In that case, what happens? So this is actually what defines canonical transformation. Now, if this is a canonical transformation, which does not depend on time explicitly, then it is called restricted canonical transformation. Okay. Now, f can be a function of coordinates old, new, momenta, old, new. All right. But generally, it's a function of only two items at a time. For example, so here it says f is a function of half old and half new variables, because f is actually helping you make something which we have already talked about earlier called Laplace transformation. So f is a function of half old and half new variables. All right. So if f1 is a function of old coordinates and new coordinates, then substituting df by dt as dou f1 by dou t, dou f1 by dou q, q dot. It should have been q dot. That dot is missing here, the typography. plus dou F1 by dou Q, capital Q times Q dot. And now what you can see is the left hand side, you can correlate with the right hand side and see how they must be related. So if you compare them, then you can see the coefficient of Q dot. In this case is dou F1 by dou Q has to be small p, and coefficient of capital Q dot, all right, in this case dou F1 by dou capital Q has to be minus p. So capital P becomes minus dou F1 by dou Q, and your K becomes H plus dF1 by dt. That's your d Hamiltonian. All right. So many times either you know how the coordinate transform or you have the generating function f. If you have generating function, then you have to find what the transformation is like. Or if you know transformation, then you can actually figure out what the generating function is in principle. Okay? Every time it may not be very easy, but you can in principle figure out what is the generating. So there is again a sort of typography because oh, done this. Yeah. So inverting for Q's, your new coordinate is a function of old coordinate and old momenta. And using this new coordinate and F1, you can find new momentum as minus dou F1 by dou Q, so that you get new momentum as a function of old coordinate and old momentum. So the first line shows you first half of the transformation, second line is second half of the transformation. Now here we have restricted to symbols Q and Q, P, but depending on number of particles, number of degrees of freedom, you can have, say, for example, n Qs and n Ps. All right. So you'll have Q1, Q2, Q3 up to Qn, P1, P2, P3 up to Pn, and there will be corresponding n new coordinates and n new moment. So if you know capital Q and capital P, then F1 can be arrived at. For example, if you look at the transformation, uh, small q equal to capital Q raised to half e raised to minus capital P, and small p as Q raised to half e raised to capital P. Then by making a small adjustment. In fact, if you multiply the two, small p into small q, it is capital Q, because e raised to minus p and e raised to plus p cancels out. So that new old momentum is new coordinate upon old coordinate, capital Q upon small q, and new momentum, capital P, will be half log capital Q, new coordinate, minus log of small q, log of old coordinate. Okay, and therefore, from the definition of generating function f1, if you have seen earlier, your dou f1 by dou small q is supposed to be p. In this case, that is q by q. And dou f1 by dou capital Q is minus capital P. In this case, that's log q minus half log q. So you have these equations. Now, if you integrate the first equation, that will give you, with respect to small q, it will give you q log q plus an arbitrary constant, which could be function of capital Q, the f of capital Q. To satisfy second equation, okay, which is dou f1 by dou q, log q minus half log capital Q. Remember, that's minus p, okay? P was the other way we have written. So you must have f1 as q log q minus half q log q minus capital Q. Okay, then it would satisfy this both the equations. And in that case, yeah, so we figured out the generating function. So using definition of the generating function f1, oh, we have done this, sorry, right here. So suppose if f was f2, function of old coordinates and new momenta, then also you can go through the same procedure, and df2 by dt, you can write as dou f2 by dou t plus dou F2 by dou small q, because it depends on small q, times small q dot, and dou F2 by dou capital P times P dot. And of course, matching the coefficients, you will get these equations. The old coordinates as dou F2 by dou old coordinate q, and new coordinate as dou F2 by dou new momentum. All right. And of course, the Hamiltonian relation is standard one as usual. And you have similarly two more, which relates where f your generating function depends on old momentum and new coordinate, or new momentum and new coordinate, or old momentum and new momentum. And in that case, you will have corresponding equations as you can see it on your screen. Okay, you have to go through the same process as what we did in case of F1 and F2 to realize that these are the equations that you will get here. Okay, I'm going to go to the next. So, in a nutshell, this is a box which shows you those four transformations. They are the example shown in the third column. Okay? It's a trivial special cases. And amongst them also, if you look at F2, F2 is an identity transformation. You can see your new coordinate is same as old coordinate, new momentum is same as old momentum. Even F3 is an identity except that it reverses the sign, nothing else, right? But you can see the corresponding generating function that would do that because you are already given the equations and the derivatives. You can also derive yourself for yourself that that's what you will get. All right. Okay. I'm going to go to the next slide. So it may not always be possible to express canonical transformation in these four basic types of Legendre transformations. Okay. So we may end up with generating functions which are zero or indeterminate. And a suitable generating function doesn't have to confine to one of these four basic types for all the degrees of freedom. In fact, it's possible that for some degree of freedom it is of one type, and for other degrees of freedom it is of the other type. So in that case, it will be mixture of the two types, if, or more than two types. Okay, a mixture of one of those or more than one of those four types. So for example, here you are given an example, Q1, P2, and capital P1 and capital Q2. Right. So for the second coordinates and old momentum and new coordinate, but for the first coordinate, it is old coordinate and new momentum. Right. So in that case, your generating function has to be of the type shown here, and it would have corresponding equations which would obey what you see on your screen. P1, small p1 is dou f dash by dou q1, small q1, of course. Capital Q1 is dou f dash by dou capital P1. Small q2 as minus dou f dash by dou p2, and capital P2 as minus dou f dash by dou capital, with of course the standard relation. Okay. So I've already told you about the F and F3, which are identity transformations. Or the second one is an example where you have a mixture of the two types of F1 and F2. So actually, capital F relates, F depends on old coordinates and new momentum for the first particle or first degree of freedom, and old coordinates and new coordinates for the second degree of freedom. So for second degree, it is of F1 type, and for first degree, it is of F2 type. So here it should have been actually F2 plus F1. Yeah, it should have been F2 plus F. I will take an example of harmonic oscillator problem. So you can see the Hamiltonian is kinetic energy plus potential energy term. And actually, if you take 1 by 2m common, then the two terms inside are both perfect squares. And to solve this problem, let's say because there are perfect sum of perfect squares. Sum of perfect square reminds you that you want to simplify the problem, you should have something like cosine function and sine function, because their squares add up to give you one. So let's say old momentum is some function of new momentum plus cosine of new coordinate, and old coordinate is some function of some means same function of new momentum upon m omega times that m omega comes because of this scale factor m square omega square 6 times sine of new coordinate. So if you substitute, actually that plus sign should have been equal to. So then your Hamiltonian becomes square of function of new momentum divided by 2m. Obviously, you can see it does not depend on new coordinate capital Q, which means capital Q is cyclic. If capital Q is cyclic, coordinate is cyclic, then conjugate momentum, in this case capital P, would be conserved quantity. It is constant. And then if you look at the Hamiltonian, which is square of function of new momentum upon 2m, and new momentum is constant, then that Hamiltonian is also a constant of motion. All right. Now to get this form, of course, how do you decide this? It comes from some trial and error, because there is no straightforward rule which tells you. But let's try something like half m omega q square cot q as your generating function. So you can see it's the first type, because it is dependent only on old coordinates and new coordinates. And so this will give you old momentum as m omega q cot q, and new momentum as m omega q square by 2 sine square. Now, you know what is small q? Uh, yes. Uh, so you can correlate the third line on the screen with the second last line or the sixth line. That will allow you to guess what is your f of p. So your f of p actually is root 2m omega p, uh, related to that, and so on. So your small p becomes actually root 2m omega p cos q, and small q becomes root of 2p by m omega sine q. F of p is root 2m omega p, by just comparison, by just matching the equations shown. All right, I'll go to the next. So that's what was the last line on the previous slide. Again, I'm saying there should have been equal to sign here. All right. So your Hamiltonian has, because of this transformation, becomes omega times p, new coordinate. And your q was cyclic, and q turned out to be omega t plus alpha, as we have seen earlier. All right. If your h represents total energy, all right, then your momentum p, new momentum, is e divided by omega, and new coordinate derivative is dou k by dou p. In this case, k is omega p, so this will become simply omega. And then if you take the integral, q will be omega t plus alpha. And so q is omega t plus alpha, you see there is a cos q and sin q, you can substitute there back. And so in terms of energy, you get old coordinate and old momentum. So we have solved the problem without actually solving differential equation. With this technique, it became easy to solve the problem without actually solving differential equation by making some small transformation. All right. But if you take the solution of this kind, a sine omega t plus alpha and b cos omega t plus alpha, actually they represent ellipse in phase space. Okay? You look at the energy equation. which is like x square by a square plus y square by b square equal to 1 if you do some small rearrangement. And in that case, area of that ellipse, it will be clear in the next slide why we are talking about area of the ellipse. In phase space, which is pi AB. So if your standard ellipse is x square by a square plus y square by b square equal to 1, then the area of the ellipse is pi AB. In this case, that because of your A and B, the ones which are sitting next to cosine and sine, becomes 2 pi E upon omega. All right. So let's look at the next slide. Right. So if you see the picture here, the figure A, top left, is your old momentum, which varies as cosine function, cos omega t plus alpha. B, the second graph on the left, middle graph on the left, is a old coordinate. It goes as sine function of time, sine omega t plus alpha. The last graph, third on the left hand side, is the ellipse in phase space. All right, it's a graph of Q versus P for constant energy term. So if you vary the energy, if you change the energy, you get a second ellipse. Or different energy values will correspond to different ellipse. All right, so that's an ellipse here. The top right graph is new momentum as a function of time. But you know, new momentum is constant and it turns out to be E by omega. That's a constant. And your new coordinate is omega t plus alpha. So this intercept here on y-axis here is alpha and it's omega t. So it is a straight line with slope omega. Now here the last graph on the right hand side is the new momentum as a function of old coordinate. All right. But it doesn't depend on old coordinate because it's a constant. E by omega. So it's a constant. Right? In quantum mechanics, we'll not go into detail of the physics behind all this, but in quantum mechanics, for a simple harmonic oscillator, your energies are multiples of h bar omega. So if you take E as h bar omega, then the area of ellipse turns out to be h. Okay? So that is basically the area for one-dimensional oscillator in phase space. Area in phase space of one-dimensional simple harmonic oscillator in quantum mechanics. Right. So what we will do is we will stop the session here on canonical transformation. I'll have another video for Poisson vector.